Hi, if you saw my previous video, I got a package from Lei Chi Hung, and he sent me a passive probe, but I thought we'd take the board he gave me and the little RF box, a little shielded box, and have a play around with an LC pi filter. Why? I don't know. Why not? I just wanted to basically show off the performance of such a filter and how to use a spectrum analyzer basically with a tracking generator to get the response of such a filter like this. So I'm on a website here. This is calculatoredge.com, and they've got an online filter for a low pass LC Butterworth pi filter, and if you have a look here, you can see it's pi shaped. If you just ignore L2, C3 and all the rest of those through there, if you just look at C1, C2 and L1, you can see it's actually a pi shape like that, and that's why it's called a pi filter. It's also called a capacitor input filter because it's got a capacitor on the input. But yeah, I think it's more commonly known as a pi filter due to the shape. So I thought, well, what if you wanted to say do a LC filter, pi filter like this? It's a single stage. We only do a single stage one because the board that Lei Chi gave me only supports a single stage on there. So let's say you wanted to do, say, a 20 megahertz filter. That'd be 3 dB down, of course. Cutoff frequency of filters is usually always measured at the -3 dB point, and let's do 50 ohms because our spectrum analyzer tracking gen output and spectrum analyzer input is all 50 ohms. So, well, that's the impedance of the load. So the number of components we want is 3. So we've got a 3-component design here, and let's calculate what values. There are standard formulas for this. It's going to vary depending on your PCB, parasitics, and stuff like that. But we get a value of 795 nanohenries. Let's convert it to microhenries, which you're probably more familiar with. 0.8 microhenries and 159 picofarads, or puff, as it's called in the trade. Now, I don't have that exact value. I've only got, say, a 1 microhenry inductor in my standard kit. So let's call that, say, 15 megahertz. Let's try that again. Recalculate it. There we go. Bang. 1 microhenry, pretty close, and 212 picofarads. Let's change that to a standard, E12 type range. You can get a 220 picofarad capacitor. I'll have those in my kit. So let's build up a pi LC low pass filter with 220 picofarad capacitors, both of them, and a 1 microhenry inductor, and see what happens. We should be able to measure a -3 dB cutoff point of around about 15 megahertz, give or take, based on the component tolerances and some parasitics on the PCB as well. Let's give it a try. So here's our little low pass pi filter here. We've got our 1 microhenry inductor there. We've got a couple of links here because there were extra components on the board there, and we've got our 220 picofarad ceramic cap there and there. So you can see the pi shape in that. This is the ground along here, and this is the input over here and output over here. Let's give it a go. So what we're going to use here is our Rigol DSA815 9 kilohertz to 1.5 gigahertz spectrum analyzer with tracking generator option, and this is absolutely vital. You need one of these tracking generator options to measure the frequency response, the frequency performance of filters and other circuits like this. So if you're going to buy a spectrum analyzer like this is like a $1,200, $1,300 base model without the tracking gen, but spend like an extra $300 and get that tracking generator option, because if you don't get that, you can't do any of this, or it's incredibly difficult. So the tracking gen is well worth the money. Trust me. Now what this tracking generator does is that when the spectrum analyzer takes the sample at a particular frequency, because instead of an oscilloscope, which is time domain, this is frequency domain, it at a particular frequency which it's measuring that signal at, it outputs that exact same frequency on the tracking generator output as it sweeps across. So effectively this is an RF sweep generator. It starts at the low frequency and goes all the way up to, and it depends on the displayed frequency. You know, if we're over the full range like we are here, 1.5 gigahertz, 750 megahertz center, basically from 0 to 1.5 gigahertz, then it's going to sweep over that entire range on the tracking generator output. And it's that sweep, frequency sweep, which allows you to get the frequency response of your particular circuit under test. Anyway, what we're going to do is turn on our tracking gen here. I don't know why that button, you can't just press it twice and it automatically switches it on. I don't know, that just would have been nice. Anyway, we're switched on our tracking gen here. Our level is going to be 0 dBm, fine. We don't want a power sweep off. The power sweep, we just want a constant output voltage level from this thing. So we'll go into frequency, well, we'll go into span here and we'll set full span. So we're doing our full 1.5 gigahertz span here. So our center frequency down here is 750 megahertz. We're going over the full 1.5 gig range or thereabouts. So let's go into Amplitude. And by the way, I've got just the tracking gen joined straight through to via a 50 ohm coax straight to the RF input. And of course the tracking gen output is 50 ohms and the RF input is 50 ohms impedance as well, and that's what we calculated for our pi filter here. So we're going to go into Amplitude here and we'll just auto scale that, and look at that. Isn't that funny? What do we expect? We actually expected, well, here's the reference level over here, 0 dBm. We expected that to be flat across the whole range because we've just got a coax in there. We've got no other circuit. So in theory, you know, this coax can, you know, it should be able to do 1.5 gig. I mean, not all coaxes can, but you wouldn't expect to see all that garbage in there. You'd expect a flat line. Why aren't we getting it? And the answer's really easy. Go check the manual for this thing. And if you take a look at the tracking generator option output, you can see it's rated for plus minus 3 dB output level over the entire 1.5 gig frequency range. So it's not a great tracking gen at all, and that's not terribly surprising. It's not easy or cheap to make a completely flat and linear tracking gen from, you know, DC to daylight, basically 1.5 gigahertz. I know that's not daylight to the RF guys out there. Heck, you know, anything under 1 gigahertz is DC as far as they're concerned. But anyway, it's not that easy or cheap. So what you're buying here is a spectrum analyzer, and you're not really buying that good a tracking gen. You're only paying a couple $100 for it. Its performance is not going to be completely rule of flat over the entire frequency range, and this is the actual performance of it, believe it or not, because the spectrum analyzer input, of course, is going to be pretty good. This is a, you know, a reasonably decent spectrum analyzer. So if we had a better rule of flat tracking gen, we would see a rule of flat line. But because the tracking gen's not that great, this is what we get. Now, how do you measure? I mean, you know, the amplitudes here, I mean, it's spec'd in the manual as plus minus 3 dB, so it's well within that. I mean, you know, we're only talking sort of a peak around 1.3 dB there, and minus 1.7 or thereabouts dB over the entire range. How do we fix that? Well, Rigol know that this is a problem. So you go into tracking gen here, and you use what's called the normalize function. And that basically compensates for the poor performance of the tracking gen. So what it can do is it can store this waveform and then subtract it from your final signal to give you a proper response. And it has this capability built in. It's easier and cheaper to add this capability in software than it is to design and build a rule of flat tracking gen on this thing. So what we want to do, you use your coax directly input and output. So before you take any measurements, you compensate for the tracking gen. So you just store it and you turn normalization on. Oh, it didn't like that. Press it again. There we go. It's updating the reference trace, and bang, there's our rule of flat response. So now we can disconnect this and we can plug our circuit in series with it and test it, and it will automatically compensate for that stored reference. It'll normalize it. So what we want to do here is go into frequency, set our setter frequency to say 10 megahertz or thereabouts, and the frequency span, okay, let's just do 20 to start off with, and we'll take our little filter here and we'll plug it in series here with the input. Ta-da, there it is. Okay, so we've got a filter in here, and let's try and measure the response of this thing. And bingo, look at what we get. Look at, here's our filter response dropping off there. This garbage here, I'm going to say that's from setting up the reference level. We did it over the full span range. We could redo the normalization across a smaller range, and we should be able to get rid of that. But I just want to show you the roll. So let's just assume that that's flat. Okay, so let's change our frequency span here. It's currently set to 20 megahertz, so this is 0 to 20 megahertz here with a center frequency of 10 megahertz, and let's expand that, and we can see where it gets minus 3 dB down. Actually, we'll try and measure that with one of the markers. So how we do that is we just hit marker over here, and we've got various markers in various modes, but here's the little marker, number 1, and it tells us, and we can use the knob over here to move that back and forth. So we want minus 3 dB, and we're expecting around about 15 megahertz for that. And what do you know? Pretty darn close. Look at that. Ah, magic, 15.06 megahertz. So we've accurately measured the minus 3 dB roll-off point of our LC pi filter here. So let's have a look. Let's expand. Let's go into span here and expand this range. I'll use my knob again, and you can see the change in value. I could type it in. I can just type in a value on the keypad here if I wanted to, but let's just use the, let's just increase it to 30 megahertz, and you can see it's going off here. So let's rescale that. Let's just auto scale that. There we go. And let's expand that span again. Let's go up in frequency. You can see it's rolling off nicely. Beautiful. And it's starting to level out, actually. There we go. We're up to 100 megahertz span now. So this is 100 megahertz, and you'll notice it's actually going back up. Look at that. And if we keep increasing our span, we're at almost 300 megahertz now. Look at this. Isn't this interesting? You know, we're at 600 megahertz span there, and you can see the fall off of our filter, but it hasn't just continued to fall off like a brick wall. It's actually recovered. It's reversed and is, you know, we're talking minus 17 dB, that minus 15 dB up here. I mean, it was down to around a minus 27 dB there, but it's gone back up, and it has a response like that. And of course, if we go over the full 1.5 gig range of this spectrum analyzer, it rolls off and it recovers like that. Why is it doing that? So what's causing it? Let's take a look at our circuit here. We've only got basically 4 components on this entire thing. I know you're thinking, well, there's only 3. No, there's actually 4. There's the inductor, of course. We've got our 2 capacitors plus the circuit board as well. Remember, circuit board is a component like anything else. It has a dielectric constant, acts as inductance, capacitance, all sorts of stuff like that when you start getting up into high frequencies. But this is FR4. It's going to be more than good enough, especially at the 70 megahertz that we're seeing this thing change on us. So we're using NPO ceramic capacitors here. They should be more than good enough for this sort of frequency range. So you go, aha, the inductor. So let's take a look at the inductor I used.
And this is what I used. I had it in my kit here. It's an NLC 453232, 1 microhenry, but it's basically a power inductor. It's not designed for RF stuff. So what we're seeing is the low-ish self-resonant frequency of this inductor. It is not a good inductor at high frequencies. It doesn't work as it's supposed to. And that's exactly what we're seeing on the spectrum analyzer here. So we can see it here. There, I've got my marker there. You can see the little 1 going around, and it's reversing there at about 65 megahertz. So that's going to be around the self-resonant frequency of this inductor, i.e. where it rolls off and stops becoming the inductor you expect it to be. And then you get into all sorts of parasitics because it's wire wound. There's a whole bunch of wires in there wound around, and you get interwinding capacitance and all sorts of stuff, and it's not working as the inductor it was down at these lower frequencies below 70 odd megahertz there. Now let's try a slightly different one, the NLC 322522. Once again, 1 microhenry. Let's see if that changes that self-resonant frequency point. And you can really see the wire wound nature of this one. The other one was fully encapsulated, so we couldn't see it. But this one here, you can clearly see the inductive winding inside this thing and exactly how many turns it's got. And if I just disconnect the filter here, so we've got nothing going in, you can, bingo, see the noise floor of the unit down here. Okay, I've soldered the new inductor in there. Let's plug it in and see what we get. We're exactly the same as before. No, we're still on around about 70 megahertz there. Bummer, I was hoping we'd see at least a bit of a difference. But I managed to steal this one off a old VGA video card, and I measured that at 500 nanohenries, so half a microhenry. So it's, it's going to adjust our frequency somewhat. All right, let's give this one a try here, and let's have a look. Bummer, it's still around that 70 megahertz mark. All right, let's try one of these SMD ferrite beads. Once again, salvaged from a board. I have no idea of its value, but let's see what it does. Hey, it's not better. The frequency has changed though. We're now about 125 megahertz before it starts bending back there. But certainly its performance is pretty terrible up at the high end up here. I mean, we're only talking, well, it's, peaking around -7 dB. Awful. But really, all that experimentation is for naught because we are not going to escape this characteristic notch response. You can see how it goes down and then recovers. That's called a notch response in our low pass filter there. So it's not working nearly as good as a low pass filter up at the high past a certain frequency point. So when you're designing one of these filters, you will design it for that particular frequency which you're trying to attenuate at best there, and because after that it's just going to recover and it's going to have that notch type response. And this is actually characteristic of one of these LC pi filters. You can't escape it. The only way to escape that notch response is to change to a different type of filter, either a T-type filter or a multi-stage filter or something like that, to really attenuate this high-end stuff, because it all has to do with the parasitics of the inductor and the parasitics of the board and everything else in there. It's just totally characteristic of a very simple LC pi filter. Nothing you can do about it. Hey, but it was fun trying a few different values anyway. And I'll just show you another thing with the noise floor here. I've got the full frequency range here, 1.5 gigahertz. So we've gone into span, we've gone full span there, and we're in the amplitude, we're auto scaling that, and you can see it's around about -65 dB. I've got no normalization on here, and you can see that it's around about that figure. But there's an RF preamp you can switch on, and if you go into RF preamp here and switch that on, you'll notice noise floor, bang, goes much, much lower. And if you want to know if the switching on the tracking gen makes a difference to the noise floor with the preamp on, very little. Watch this. There we go. It's just slight. You can see a slight difference there by switching on the tracking gen. So that'd be the internal crosstalk. So I hope you like that. That was just a bit of a small play around with an LC pi filter and measuring its response on a low-end spectrum analyzer with a tracking generator output. There are other ways to do it, of course, with your SIGGEN and your oscilloscope and stuff like that. And there are ways to do it without the tracking gen option in the spectrum analyzer, but it is actually quite hard. But with that tracking gen option, you can see how easy it is. And perhaps we can follow this up later with different things, but it's worth playing around with something like this. It was good fun. So I hope you liked it. If you want to discuss it, jump on over to the EEVblog forum. And if you do like it, give it a big thumbs up. Catch you next time.